Hello. In the last many lectures, I discussed about phase equilibrium in detail. To complete this topic, we have to take up an interesting law called Nernst distribution law. Although it doesn't involve any phase diagram, it has many practical applications, and we deal with equilibrium between different liquid phases. Today's lecture plan goes like this. I'll introduce you to the topic. We'll look at what happens when solutes get distributed between immiscible liquids, the resulting law, which is known as Nernst distribution law, conditions for validity of Nernst distribution law, and then look at the thermodynamic derivation of this law. There are special cases, two of which we'll be seeing. One is association of the solute in one of the solvents and dissociation of the solute in one solvent. Immiscible liquids. We have dealt with systems involving immiscible liquids earlier. What we have seen then is its application in steam distillation. But here we deal with these systems from another angle. Some of the examples of immiscible liquid pairs are carbon tetrachloride, water, chloroform water, and carbon disulfide water. And we also come across immiscible liquids of molten metals as immiscible liquids, molten lead and molten zinc. So, a simple experiment was carried out by Berthelot and his co-worker in 1872, in which solutions of iodine in carbon disulfide of different concentrations were mixed with distilled water thoroughly, and when it was analyzed for iodine, it was found that iodine gets distributed between the two liquids in such a way that the ratio of its concentration in the two liquids is constant, irrespective of the original concentration of iodine taken in the experiment. And these experiments were, of course, carried out at constant temperature. Several such studies were done later, each involving a pair of immiscible liquids and different solutes, and more or less similar results were obtained. The results obtained by Berthelot and co-worker is of this type. Concentration of iodine in carbon disulfide layer divided by concentration of iodine in water layer is equal to C1 by C2. That is taken as Kd, which is a constant and is termed as the partition coefficient or the distribution coefficient. However, extensive studies by Nernst showed that in many cases C1 by C2 is not found to be constant. Only when the solute has the same molecular condition, that is the same molar mass in the two solvents, we are likely to get a constant ratio. That's how he came up with what is now called Nernst distribution law. This is the photograph of Nernst, who has made lot of contribution in physical chemistry. If a solute partly associates to form double molecules, that is dimers, in one solvent but not in the other, the simple ratio C1 by C2 is not a constant. However, if the ratio of concentrations of only the single molecules, that means we are excluding the dimer concentration in the two phases, then C1 by C2 is found to be constant. As an example, we can consider the behavior of acetic acid and benzoic acid. These have a tendency to form dimers in benzene. So, if we carry out an experiment in which these acids are distributed between water and benzene, then the results of the experiment C1 by C2 are found to be not constant. But if we consider the concentration of only the monomers, we get a constant ratio. That means if we have to consider the concentration of single molecules. The Nernst distribution law is valid only for concentration of single molecules. We have to stress that means in the two phases. Therefore, if the total concentration of benzoic acid in benzene is taken, the law will not hold good. The statement of the law. When a solute distributes itself between two immiscible liquids in contact with each other, there exists for similar molecular species at a constant temperature a constant ratio of distribution between two solvents irrespective of the total amount of the solute and irrespective of any other species which may be present. There are certain conditions for the validity of Nernst distribution law because it is a simple statement which is made and we have to take into account whether there is any change in the molecular condition of the solute. There are two essential conditions or prerequisites for validity. One is the temperature should be constant, of course, because the solubilities of solutes in liquids depend on temperature. Second condition is existence of similar molecular species in the two liquid phases in contact with each other. In addition, there are other conditions also to be met for the full validity of the law. It goes without saying that solution should be dilute. As the concentration increases, deviation from ideality sets in. Therefore, if the higher concentration solutions are taken, there will be larger deviations. And in the extreme case, the both solvents may get saturated with respect to the solute so that the result that we get for Kd will be Kd equal to S1 by S2, where S1 and S2 are the solubilities of the solute in the two phases. The equation will be strictly valid only, 1, when the solute is not highly soluble in both the solvents. That means it should have limited solubility in the two solvents. And if the two liquids are mutually immiscible or only very sparingly miscible, and their mutual miscibility is not altered by the presence of the solute, which means if there is some liking for each other, in such a case, the law may fail. We should insist that when the solute is added, the nature of each of these liquids will change to some extent, which may increase the miscibility. That should not happen. Therefore, the experiment has to be carried out at very low concentrations of the solute as far as possible. We can derive Nernst distribution law from thermodynamic considerations. Let us consider a system in which solute A is present in the two immiscible liquids 1 and 2 which are in contact with each other. Suppose further that the chemical potential of the solute in solvent 1 is mu1 and in solvent 2 it is mu2. When the two phases are in equilibrium, their chemical potentials will be equal to one another. That is, mu1 is equal to mu2. So, the term chemical potential is not new to you. You have come across that in thermodynamics as well as while deriving phase rule equation. Just recall that. We know that from thermodynamics, mu is equal to mu0 plus RT ln A, where A is the activity. Therefore, we can write for phase 1, mu1 is equal to mu1 naught plus RT ln A1, and for phase 2, it will be mu2 equal to mu2 naught plus RT ln A2. Since the two are in equilibrium, we can equate mu1 naught plus RT ln A1 equal to mu2 naught plus RT ln A2. In other words, RT ln A1 by A2 is equal to mu2 naught minus mu1 naught. Now, at constant temperature, the standard chemical potentials mu1 0 and mu2 0 are constant. Since R is also a constant, it follows that A1 by A2 is also a constant. Always we have to consider constant temperature. We also have taken care to keep the solutions dilute, and in such conditions they behave ideally, and hence Henry's law, according to which activity is proportional to mole fractions, is obeyed in each phase. It follows from it that A1 by A2 is equal to K1 x1 divided by K2 x2 equal to constant at constant temperature. In this, x1 and x2 are the mole fractions of the solute in the two phases, and K1 and K2 are the Henry's law constants for the solute in the two phases. Therefore, we can write x1 by x2 is equal to constant. It is also known that solutions are dilute. The ratio of mole fractions is almost the same as the ratio of concentrations, and hence we can write x1 by x2 is equal to C1 by C2 is equal to constant at constant temperature. Thus, if a substance is present in two liquid phases in contact with each other, then at equilibrium C1 by C2 is equal to constant. We denote it as Kd, the distribution coefficient. This is nothing but the Nernst distribution law. Now let us look at the special cases where the solute may not behave as simple molecule. Let us take case 1, in which association of the solute in one of the solvents takes place. That means in one solvent it behaves normally as, say, solute you can see as X. In the second solvent it forms an associated molecule. Let's see. Let X represent the molecular formula of the solute. Assume that it remains as such in phase 1 as we have seen, in which let its concentration be C1, and in the second phase it largely associates to give the molecules of Xn times, that is in phase 2. If the associate molecules will exist in equilibrium with single molecules as shown earlier, let C2 be the total concentration of the solute in this phase. So in phase 2 there exists an equilibrium between the associated molecules and single molecules represented as Xn times in equilibrium with Nx. Applying the law of chemical equilibrium, we get K, the equilibrium constant, is equal to concentration of X raised to N divided by concentration of Xn. That means concentration of the single molecules divided by concentration of the associated molecules in phase 2. We can rearrange this equation so that we get concentration of X is equal to nth root of K into concentration of the associated molecules, that is equal to constant into nth root of concentration of the associated molecules. So if the solute exists largely as associated molecules, which is generally the case except at large dilutions, the concentrations of the associated molecules, that is Xn, may be taken as equal to C2, the total concentration. That is, concentration of Xn is equal to C2, and therefore X is equal to constant into nth root of C2. Since the distribution law is valid only if the concentration of similar molecular species in the two phases is considered, it follows that C1 upon concentration of X, that is given as earlier is equal to constant. That is, C1 divided by nth root of C2 is equal to constant, denoted by Kd, the distribution coefficient. So, instead of a simple ratio C1 upon C2 giving a constant value, when there is association of the solute in one of the solvents, then the ratio C1 upon nth root of C2 is a constant. For example, in the case of benzoic acid, when it forms a dimer in benzene, it is C1 upon under root C2 we get as a constant. Let us look at case 2. What happens if the solute undergoes dissociation in one of the solvents? You can see in the figure that solute X has a concentration C1 in phase 1 where there is no dissociation, and in phase 2 it undergoes dissociation into A plus B. As in the earlier case, let X be the normal formula of the solute. Let us assume that it remains unchanged in liquid phase 1 but undergoes dissociation into A and B in liquid phase 2. Let C1 be the concentration of the solute in phase 1. That means it is the concentration of undissociated molecules of the solute. And in phase 2, let C2 be the concentration of the solute. C2 is the total concentration actually. It includes the concentration of the molecules remaining unchanged plus the molecules that undergo dissociation. But we know that Nernst distribution law is valid only for the ratio of concentrations of similar molecular species in the two phases, that is, of undissociated molecules only. Suppose alpha is the degree of dissociation of the solute X in phase 2. Then the concentrations of the various species can be given as, we have the equilibrium X getting dissociated into A plus B. The respective concentrations are for X C2 into 1 minus alpha, and for A and B it is C2 alpha and C2 alpha. Therefore, according to the distribution law, where we consider the concentration of only the undissociated molecules, C1 upon C2 into 1 minus alpha is equal to Kd. It is not just C1 upon C2, it is now C1 upon C2 into 1 minus alpha that will give us the constant value, that is the distribution coefficient. Let me summarize what we have seen today. We started with how a solute behaves when distributed between two immiscible liquids. The initial experiments carried out by Berthelot, and then how Nernst's experiment showed that the validity of the law depends on the behavior of the solute in the two liquids. That means the conditions of validity have to be met for the successful application of Nernst's distribution law to any system. Then we looked at the thermodynamic derivation of Nernst's distribution law. There are special cases. Two of the special cases we have seen: association of the solute in one of the phases and dissociation of the solute in one of the phases. In my next lecture, I'll take a special case in which the solute molecule has a tendency to form associated molecules with the solvent molecules. It is a special case and will be very interesting to look at. Also, I will be taking up the application of Nernst distribution law. There are many applications, and the most important one of them is the solvent extraction, of which you have seen an example in the case of silver extraction from argentiferous lead earlier.